All right, welcome everybody. Let's get started. Welcome to this class in Mathematics 1. Before we start, a quick organizational announcement. Once again, we'll have to change rooms. For tomorrow's lecture, so Tuesday, 28th of November, we'll again meet in room 2300 instead of the Audimax. Okay? Thursday we'll be back to normal, and hopefully next week we'll also be back to normal. Good. So let's start with this week's topics. After our detour to game theory, we are back in the more abstract realms of linear algebra. And this week we'll specifically discussing linear mappings and everything that is associated to that topic. So basically, let's start with the definition of linear mapping. Basically, a linear mapping is a mapping between two vector spaces. Usually for us that will be some r to the n, possibly two different r to the somethings, one for the domain, one for the codomain. But you could use any general vector spaces. It doesn't really matter much. Right? So you have a mapping between two vector spaces, oops, like that. And the main property of a linear mapping is that it is compatible in a certain way with the operations in a vector space. And by compatible, what I mean is it doesn't matter whether I carry out an operation in V and then map the result, or whether I first map all elements that I need in the operation and then carry out the operations in W. The result will always be the same. Right? So it keeps the structure of the vector spaces intact to a certain degree. And more formally, the definition is this here. So you need two properties. You need that f of the sum of any two vectors is the same as the sum of the images of those two vectors, right? So it doesn't matter whether you compute the sum first in V and then map the result, or whether you first map each individual summand and then compute the sum. And formally, those two are different operations, right? This is the operation in V, this is the operation in W. Doesn't matter much if we're talking about r to the n's, but if we are talking about more abstract vector spaces or more general vector spaces, there might be quite a striking difference between those two operations. All right, and we have the same thing here. For the multiplication of a vector and a scalar. So for any scalar lambda and a vector x, f of lambda x is the same as lambda times f of x. So again, it doesn't matter whether you do this operation first and then map the result, or whether you first map the vector and then do the multiplication. A couple of basic examples. So this class of maps is one that you probably all know. That is usually also referred to as a linear map or a linear function. If you have a function from R to R, so just from the reals to the reals, because that is also a vector space that just multiplies the vector by some constant, 2 in this example. So f of x is 2 of x. That is a linear mapping, and you can easily see this by just doing the computations, right? You have f of x plus y. That's 2 times x plus y. And that's the same thing as 2x plus 2y, which in turn is f of x plus f of y. And of course, the same works for this lambda x, right? Because it's just 2 lambda x. And here we have multiplication in the reals, so the order doesn't really matter. You can rearrange that any way you want. And that means I can write it in this way. And this is just lambda times f of x. So this is a linear mapping. Just as a quick word of warning, often mappings of that form here are referred to as linear mappings. So some constant times x plus some different constant, right? The graph of those looks something like that. right? And this is usually, this is the B part here. So you have a translation, a line in the translation. This is a linear mapping in this sense here, if and only if B is 0. Right, so the line that I've drawn here is not really the graph of a linear function. This here is the graph of a linear function, right? That is linear. This here is not. Right, so you can't have that translation. And of course the problem is with this addition property here. If you try to compute f of x plus y, then this is not troublesome, but you only get this factor b once. And on the other hand, if you split it up and compute f of x plus f of y, you get a factor b twice. And that's the same thing only if b is 0. Right? So please don't confuse this. The term linear function is often used for functions like this as well. Strictly speaking, this is not a linear function if b is not 0. All right, so usually I'd use the term affine or affine linear function for something like that in an analogy for affine vector spaces. You remember an affine space is basically a translated vector space, so an affine function is a translated linear function. Okay, a couple more interesting examples. So here's a mapping from R2 to R2. And a simple way to define a linear mapping is through a matrix. So you can do something like this. The vector xy is mapped to a matrix times xy for a matrix of suitable size. And suitable size in this context means we need a 2 by 2 matrix. And if we have that, any 2 by 2 matrix will do. We always get a linear mapping. Right? And you can just, again, do the computations to prove that this is actually correct. So any matrix, no matter the sizes, defines a linear mapping in this way. So if I have an m by n matrix, I can define a linear function that takes n vectors as the input. So the number of columns determines what I can multiply with the matrix on the right. And the number of rows determines the size of the output of that operation. Right, so I put in an Rn vector, I get an Rm vector back here. So that's always linear. And in an analogy, again, to what I just said above, sometimes we'll deal with functions of that kind here. So ax plus a vector b, right? Almost the same thing as in the reals, but now we have vectors of possibly not just one dimension. Again, that is sometimes referred to as a linear function. It's usually not, unless b happens to be the 0 vector. All right, so here is a more abstract example. In this case, we have a mapping from the R to the 4 to P3, and P3 is the space of all polynomials of degree at most 3. So of all expressions that look like this, with the A0 to A3 from the reals. And well, that function is defined in just that way. So we use the entries in that vector as the coefficients of a polynomial. And that way we obtain a polynomial from a vector with 4 entries, and the polynomial will then have degree 3 because one of those coefficients is for the constant part of the polynomial. Right? For example, f of 1, 2, 0, 1, that maps to 1 plus 2 times x plus 0 times x squared plus 1 times x to the third. Okay, so formally that's also a mapping between 2 vector spaces. That space of polynomials is also a vector space. And you can, again, do the computations like we did here and see this actually defines a linear mapping. right, and we've talked about this here already. So this is an example for those ax plus b with a non-zero b that are actually not linear. More general, here's an important property that you should remember about linear maps, and that is the image of the zero vector is always a zero vector. And that's simply true because, of course, the zero vector can be expressed as 0 times the zero vector. This is the number 0, this is the zero vector. And by linearity, that's the same as 0 times f of the zero vector. And 0 times any vector is always a zero vector, so that's going to be the result. Right? So if you look at the graph of a linear function, if you can look at the graph due to the dimensions, the zero vector should always be included in that graph. Okay, so linear mapping always maps the zero vector to the zero vector. That means if you have a function that does not have that property, it can't be linear anymore. The reverse, of course, is not true, right, generally. So if a function has a property, it still need not be linear. It could be linear or maybe not. You still have to check those two properties, right? But for the exclusion, you could use this. It's a good first check. Try to compute the image of 0. That's usually easy to do. And if it happens to not be 0, then you can be sure that this function can't be linear already. All right? A couple of properties of linear mappings. Well, those are pretty basic, I guess. First, a mapping is linear if and only if it has those two properties. And of course, you can also put these together in one property if you wish. You can say the linear mapping needs to fulfill this relation here, right? So f of lambda x plus mu y has to be lambda f of x plus nu f of y. You combine that into one property. I usually would recommend you use those two properties separately because it's often easier to see that those work or don't work. Yeah, but if you're feeling smart and you want to be quick, this is a valid alternative. We've just discussed this one. The image of the zero vector is always 0. And well, this one is more of a theoretical interest. The space of all linear mappings between two given vector spaces, that's usually denoted by lin of v and w, that is itself a vector space. So you can operate on linear mappings. And of course, you can define linear mappings on spaces of linear mappings, and then things get out of hand quickly. But that is a nice theory, actually, but we won't talk about that too much. All right, and similar to what we did with matrices, you have already seen there is some connection between matrices and linear mappings, right? A matrix defines a linear mapping, and we'll see that connection goes even deeper. One point in there is that we've defined a kernel and an image on matrices already. And we can do the same thing on general linear mappings. So remember the kernel of a matrix, that used to be all solutions of this homogeneous system of linear equations. And similarly, the kernel of a function, of a linear function, is all solutions of this equation, f of x as 0. So all the roots of that function f. That's called the kernel. And as with matrices, that kernel is a linear subspace of the domain, in this case, V. And then we also have the image. The image is, as for all possible mappings, is just defined by all possible y that can be written as the image of some f of x, right? So all f of x is where x is in the domain. Okay, so you could also say this is the same thing as f of v. And this also is a linear subspace for linear mappings, not in general, but for linear mappings it is. And this time, of course, the image lives in the codomain W. The kernel lives in V, the image lives in W. Right? So the kernel is a subspace of V, the image is a subspace of W, of the codomain. And again, similarly to matrices, let's first have a look at that similarity maybe. The kernel is basically the same thing, right? So in particular, if you define f of x through a matrix to be A times x, then that means the kernel of f is exactly the same thing as the kernel of the matrix. And similarly for the image of f is the same thing as the column space of the matrix, right? Because remember, the image of f is basically the set of all A times x, where A is in the domain V. And multiplying A by x basically means what you're doing is you take in a linear a combination of the columns of the matrix where the entries in x are the coefficients. Right? That means basically what you do is the span of all the columns of A, and that's the column space. Right? That's why the image of F is the column space of A. And finally, you remember the rank nullity theorem that we've discussed for matrices already. You will remember, hopefully, for matrices, we had the relation that n is equal to the dimension of the kernel of a matrix. So n is the number of columns, dimension of kernel, plus the rank. And the rank is just the dimension of a column space. And the same thing holds in a more general form for any linear mapping. And here you replace the n by the dimension of the domain V. Right? So the dimension of the domain is the same thing as the dimension of the kernel of F plus the dimension of the image of F. That's the general rank nullity theorem for linear mappings, and that matrix rank nullity theorem is just a special case of that. Okay, questions so far? Great, then maybe let's take a quick look at the homework before we move on. We have that here. So, 3 homework problems this time. Let's look at the first one, H71 first. For each of the following functions, decide whether they are linear or not, and if they are linear, determine a basis of the kernel and the image or basis of the image of the function. So first question here would of course be, are those functions linear? And if so, we can take a look at image and kernel. So I'll turn to tweetbat once again. And I'll first ask for subproblem A, is that a linear function? Here's the tweetback URL for this week. So let's see what you think. Give you 30 more seconds to answer that. Right, let's take a quick look. So here's your answers. Overwhelming majority said, yes, this is a linear function. And of course, you're right, this is a linear function. So this begs the question, what about the dimension or the kernel and the image of a function? I just asked for the dimension on tweetback. So let's see if you can answer that. What is the dimension of the kernel and what is the dimension of the image? Again, let's take 30 seconds to answer that. All right, so let's see the dimension of the kernel. Most of you said the dimension of the kernel is 2, and that is correct. The dimension of the kernel is 2. Quite a few said something else. Maybe we should have a look at that. And of course, if you know the dimension of the kernel, then the dimension of the image should be clear from the rank nullity theorem, right? So I'm just asking for the dimension if the kernel is 2-dimensional. And in this case, remember the space itself. So the domain is R3, so that's 3-dimensional, right? Kernel is 2-dimensional, that means the image has to be 1-dimensional. All right, so again, let's quickly go back to the vote. Most of you said just that, and you were right, of course. Maybe a very quick look at how one could obtain a basis. So for 7.1a, I'll skip the linear part because I think most of you got that right. If I'm interested in a basis of the kernel, what I have to do is I have to find all possible x1, x2, x3, where f of x is equal to 0, right? So this is the expression for f of x. And I just need to find all combinations with 0. Basically, this is a system of linear equations with just one equation and 3 variables. And you know how to solve these. So in this case, I could, for example, use x2 and x3 as 3 variables and could then solve for x1. So x1 would be 1 over 2 x3 minus x2. And that means I could express the kernel of f as well, let's see, I have 2 free variables, so I'll have a combination like this here. Right, so for x2, I have minus 1 over 2 x2 in here. x2 is, of course, itself, and there's no x3 in there. Here's the x3 and no x2. And here we have 1 over 2 x3 for the first coordinate. And x2 and x3 are arbitrary real numbers. And of course, I can also write that as the span of these 2 vectors. Right? Those are obviously linearly independent because of that part down here. So I can do that. Oops, I accidentally put an x3 in here. Sorry about that. Right, and then this set here, this would constitute a basis of the kernel of f. Okay, so that's for the kernel, and then for the image. Well, in this case, things are pretty easy. Let's go back to the problem statement. So you can see the codomain here is R. And I already know through the chronality theorem that the dimension of the image is going to be 1. Right, so Ragnality says dimension of the image of F is 3 minus 2 is 1. And if the image is 1 and lives inside this one-dimensional space R, then of course it's going to be the whole space. Right? It's a subset of R. It has the same dimension as R, so it must be equal to R. And that means a basis that I could possibly use is, for example, the number 1. Right? Any real number can be expressed as a linear combination of 1, and 1 is linearly independent. Of course, any other number will do, with the exception of 0. That would not be linearly independent. Sorry? 2 was the number of free variables. Yeah, correct. Right, so we have 2 free variables here, one equation, 3 variables, so there's 2 free variables here. And that means the kernel is 2-dimensional. Right, that determines basically the dimension of the set of solutions of that linear equation system, and that is the kernel. All right, any more questions about that? Yes. So if you want to write that in the form a times x, in this case, that would be pretty easy. So if you look at that expression here, 2x1 plus x2 minus x3. So let's write that down. Plus x2 minus x3. And you can put in any vector you want. So basically all of these, x1, x2, x3, can be from the reals. And you could express that in matrix vector form if you just write it this way. 2, 1, minus 1 times x, x in R3. Is that what you wanted to know? Yeah. So this here, in a certain way, is the matrix associated with F, or one possible matrix to be precise. We'll talk about that a little later. All right, and you can see by the size of this matrix, by the way, so it has 3 columns. That means the size of the input is a vector with 3 components. So the domain must be R3. And it has 1 row, so the output will just be 1 number. So that means the codomain is R, or a subset of R. Okay, so that's how you could do this in this simple case. We'll see some more examples of more complicated cases in a few minutes. Let's have a quick look at B as well. So here we have a function from R3 to R2. And this is defined as when you put in x1, x2, x3, and the output is x1 minus x2 and 1 in the second coordinate. So the x3 is not used at all. Well, that's completely fine, of course. And again, the question is that a linear function? So let's see if you can answer that. Again, let's take 30 more seconds. All right, let's take a look at the result here. And thankfully, most of you answered that correctly, so this function is not linear. Before we take a quick look at why that is the case, let me quickly answer two questions that have popped up here that are immediately related to this one. Actually, that was the third one, right? Could you please explain again what nullity is? So that name pops up in the rank nullity theorem. Basically, what that refers to is the kernel. So another name for the kernel is null space. And the nullity is simply the size or the dimension of the null space. Right? That's it. And the rank is the dimension of the image or the column space for a matrix. So that's where this name nullity comes from the null space. And then someone wanted to ask here in the example that we've just seen, I claimed a basis for R was just this number 1. And the question was, why is the basis 1 and not the unit vector? And of course, the answer is this is the unit vector. Right? The number 1 in R is the unit vector. Seems hopefully logical if you think about it for a second. Right? The unit vectors have size 1 in a one-dimensional vector space. The zero vector, of course, doesn't make sense, so it's just the vector that consists of this one entry. That is the unit vector in R. And again, you could use any other vector with the exception of the zero vector here. That would be fine. It's just a matter of scaling, basically. All right. So those are taken care of. Maybe just a quick look at why this is not a linear function. So f of x, I just write f of x is x1 minus x2 and 1. Why is this not linear? Well, basically pick any of the properties. Maybe I'll first have a look at the second one, f of lambda x. Remember that should be lambda f of x for every x and every lambda. Well, is that the case? Let's see. If you compute f of lambda x here, that's the same thing as f of lambda x1, lambda x2, lambda x3. And if we use this definition here, that means for x1 we have to substitute this, and for x2 we have to substitute this, right? First coordinate, second coordinate of the input. So we get lambda x1 minus lambda x2 and 1. And on the other hand, lambda times f of x is x1 minus x2 and 1 times lambda. So that is lambda x1 minus lambda x2. That looks good so far. And here we get a lambda. So the problem is these two here might not be equal. And of course, they might also be equal, so we have to come up with a specific example where this does not work. And for example, let's take lambda equals 2. Right? And then f of lambda x is lambda x1 minus lambda x2, 1. And lambda f of x is lambda x1 minus lambda x2, 2. And obviously, those are not the same. And of course, in this case, you could also make an argument by taking a look at the 0 vector, right? So I have f of 0, 0, 0. Well, what is that? That is 0 minus 0 and 1. And this is 0, 1. And this is not the 0 vector in the codomain, right? So this already shows that f can't be linear. And in this case, you could also use a sum property to get a counterexample, but I think don't have to go for that. All right, so much about that example here. And of course, as a function is not linear, it doesn't make sense to talk about the kernel or the image, so we'll just skip those. Back to properties. Now this next theorem here that we have, that does seem pretty abstract, but it actually is one of the most important properties on linear mappings, and we'll apply it in the following. So the theorem, you don't have to know the theorem, but you have to know what the implications are, and we'll talk about those afterwards. So what we have here is 2 finite dimensional vector spaces and the basis of the domain and some arbitrary vectors, same number, in the codomain. Doesn't have to be a basis, doesn't have to be linear independent, right? Just has to be the same number, no matter what we choose. We could also use the same vector over and over again. That's fine. And the theorem is then there exists a linear mapping from V to W that has the property that each basis vector is mapped to the WI that we prescribed. So basically what we can do is we can take any basis of the domain and then prescribe the images of the basis. And this defines a linear mapping. And this linear mapping is even unique. So there's just exactly one linear mapping that does this. And that means if you want to define a linear mapping, all we have to do is define a basis and then write down the images of the basis vectors. And that's everything we need to know. Because if we want to compute the image of some arbitrary vector v in the domain, what we can do then is we can determine a linear composition, of the basis vectors that represent v, right? The basis generates the whole space, so there must be some coefficients, lambda 1 to lambda n, such that this is true. The basis is linearly independent, so there is exactly one choice of lambdas that does this, right? You don't have a choice here. There's only one possible choice for the lambdas. That is what makes it unique. And then we can just use the linearity property. So by linearity, we know that f of v is the same as f of this linear combination. And then by linearity, we can split up the sum and we can take out the lambdas. So what we get is this. Right? So it's a sum of weighted images of our basis vectors. So once we know what those are, we can compute the image of every vector in our vector space. Right? And the theorem says, well, just make up your mind what you want for your basis vectors, and then the rest is determined. That, of course, makes it easy and nice to define a linear mapping. I just have to write down the images of basis vectors. And of course, I have to agree on a basis first, right? Any basis will do, but that also is part of my definition. I need to know the basis. So it's sufficient to define the values of a linear mapping on a basis of the domain. And that's what we use to find a compact representation of linear mappings. in the form of a matrix that represents that linear mapping. But before we do that, let's quickly talk about bases. But before we do that, actually, is there any questions about that part? Yes. How do we determine the lambdas? We'll see an example of that in a little while. So basically the question is, how do we get those lambdas? The answer is once we have the V, we have the basis, so we know the V1 to Vn, right? So what we get here is a system of linear equations where the lambdas are the unknowns. And if you want to determine f of v, we use this precise procedure. So we first determine the lambdas through solving that system of linear equations. That's the hard part. And then the easy part is this. We just plug those lambdas in and compute that, right? Okay, as I said, we'll see an example of that. I'd just like to quickly talk about coordinate systems first. Okay, there also has been a question on TWIPAC before that asked what is the difference between a coordinate system and a basis, and I hope I'll answer that in just a minute. So you all know one of the properties of a basis is that every vector in the vector space can be written as a linear combination of the basis vectors in a unique way. And that can be used to come up with an easy way of describing all possible vectors in a vector space. And you are used to these easy ways because you all know how to describe a vector in R2, for example, or in any R to the n. Basically, what you do here is you have the usual Cartesian coordinate system. Let's say this here is our vector. Right? Then you would say this is the vector 1, 2. Here is the first coordinate, x1. Here's the second coordinate, x2 of that vector. That choice of coordinate system, this Cartesian coordinate system that we're using here, is usually convenient, but it is kind of arbitrary. I mean, I could also come up with other possible ways to define this. In this case, what I'm using is a system that is based on these two unit vectors here. Right? So I say those are the directions of my coordinates, and 1 unit of length is exactly as long as 1 unit vector. Same thing in both directions. I could do this differently. Like, for example, I could use a system that looks like this. Right, I could maybe keep one of those unit vectors and then change the other one to not be at a perpendicular angle, but something different. Maybe that's more convenient for whatever application I have in mind. Or I could say I want the scaling different on my 2 axes. Yeah, maybe I'll use a system that looks like this, has this vector here, and then a much smaller vector in that direction. And depending on the application that I have, this might be a smarter choice for describing whatever I want to describe. So what we're concerned with here is not so much the correct choice or the best choice of a coordinate system, but more the question of what is a coordinate system? How do we work with that? And basically, a coordinate system in the plane is determined by giving the 2 directions and their lengths. So I can just use 2 vectors that make up my axis, right? That tell me what the direction of the axis is and that tell me what 1 unit means along this axis. And of course, I can do this in every other vector space. The one thing I need to pay attention to is those 2 vectors need to form a basis. Otherwise, I couldn't get every vector in the space. Right? So there might be some I can't describe, and of course I don't want that. So basically, what's the difference between a coordinate system and the basis? The answer is there is almost no difference. The only difference is for a coordinate system, I need to impose some kind of ordering. A basis is usually just a set, and the order of the vectors doesn't matter. For a coordinate system, I need to say what the first and the second and the third and so on coordinate is. Yeah, so I need to call this the first coordinate and this the second, or vice versa. It doesn't matter what I do, I just have to put down my decision somewhere. So a coordinate system is just an ordered basis, right? I just write it as a tuple, and that means the order matters now. And that's it. And of course, the coordinate system that we mostly use is going to be the one that is induced by the unit vectors. That's the usual Cartesian coordinates, or often they also be called standard coordinates or canonical coordinates. Right? So that's what we call the canonical coordinates or the canonical basis. And once I have defined a coordinate system, any coordinate system, I can represent any point in my vector space, any vector, in these coordinates. And to do that, I'll just have to come up with the lambdas for describing this vector as a linear combination of my coordinate vectors. And then the coordinates are just those lambdas. And that's it. That's called the coordinate vector associated to a vector v. And we usually write it in this way. Okay, and often instead of a coordinate system, we just speak of a basis and we'll imply that the order is the one that we write down. It's not really precise, but usually people do it like that, so we'll also do it like that. A couple of quick examples. So say this here is a basis for the three-dimensional vector space R3. That's not the canonical basis. And say we have this point. So this is in canonical coordinates, 1, 2, 3. And now I want the coordinates of that point with respect to this coordinate system here. What do I have to do? Well, I just take those vectors and I need to determine the coefficients for these vectors that I need to represent this vector. And as it turns out, I need -1 this first vector, -1 the second one, and 3 times the last one. So the coordinate vector of v with respect to my coordinate system b is this, -1, -1, 3. Right? That sounds pretty abstract, but it's actually really easy, I hope. Okay, different example, just use this other coordinate system, call it b prime, same procedure. You need to come up with the right coefficients for this linear combination, and either you can just solve this in your head, or you can take a good guess, or you can solve the system of linear equations to get the right coefficients. And it turns out these are the right coefficients. So the coordinates of this point in b prime are 2, 3, and 0. Well, I guess that's, yeah, maybe we talk about this really quickly. So here we have a vector space that is not R to the something, but instead that vector space lives inside R3. So what we have here is actually a plane that is spanned by 2 vectors in 3-dimensional space, something like that. Right? And now we're saying we are interested in vectors that live in this plane. And this v here, this is one of them. This also lies somewhere in the plane. And that means, of course, we can define coordinates of v with respect to this coordinate system here, because we can represent v as a linear combination of those 2 vectors. Right? So that is what we're going to do. Again, we need to find those coefficients by solving a system of linear equations. Turns out those are 3 and 1. So the coordinates of v with respect to this coordinate system b are 3 and 1. So even though v is a vector that has 3 coordinates, right, it can be represented by only 2 coordinates, given that I know this coordinate system already. And of course, that's true for the vectors on that plane and only for those. Vectors outside of the plane could not be represented by that coordinate system. Right? So in a certain way, you could say this is kind of an embedding of R2 in R3 in that plane. Right? So those of you who have always argued that a plane is two-dimensional and should only need two coordinates, this is the formal way to describe that correctly. All right, maybe we'll skip the polynomials. I don't think that's not that important. Okay, questions about coordinates. Otherwise, we'll take a look at 7.2. Maybe let's do that. So here's the next homework problem, exercise 7.2. We have two vectors here. And unfortunately, I named those U1 and U2. That's not a very good choice, as I just see. Those are not unit vectors. My bad. I'll have to change that. So in this case, we have these two non-unit vectors that span a vector space U in R3. So same thing as we just had. We have two vectors that span a plane in R3. And we're looking at the coordinate system that is defined by those two vectors. And our first question is determine the vector v in R3 that has the coordinates 1 and -1. And as usual, we take a quick look on TweetBack and see what you think the answer is. All right, let's take 30 more seconds. Okay, and here is your answer. Most of you said 2 - 1, 1 is the correct answer, and everybody who checked that answer is correct. So again, we have two coordinates to describe that vector because our system lives in the plane, right? But of course, the vector, the actual point in R3 has 3 coordinates, yeah? So in R3, we describe it through the usual Cartesian coordinate system, and of course, that needs 3 coordinates because you can describe every point in R3, not just the ones in the plane. And if you quickly just look at the computations that we need for that, remember these here are the coordinate vectors in our system. And the vector having these coordinate means we have to take the first vector here once. Let me just use some color here. So this here refers to the first vector. And this here refers to the second vector. We have to take that minus once. So what we get here is v is 1 times this first coordinate vector plus -1 that second coordinate vector. Oops. Right, and if you do the computations, that turns out to be 2 - 1 and 1. Okay, so that is a description of v in the canonical coordinates for R3. Okay, so this way, if you have a coordinate vector, you want to obtain the actual point in a maybe richer vector space. That's the way to do that. B asks for the reverse. So the question here is determine the B coordinates of a vector W given as -1, 3, 2. So maybe let's again see what you've got. Here's the tweetback quiz. Oops, that's the wrong one, sorry. Wanted to show you the URL, of course. That's better. All right, again, let's take 30 more seconds. All right, so here's your answer. Most of you said the B coordinates are 2, 3, and you will be correct. The B coordinates are 2, 3. Just to be sure, how do we solve this? So now our vector is given in canonical coordinates, -1, 3, 2 in R3. And we want to write it as a linear combination of the two B vectors that we have. Right, so one is 1, 0, 1, and the other one is -1, 1, 0. So we need to find the correct factors here to represent this vector. And to do so, we could just solve a system of linear equations, or we can quickly do this live. So let's see. In this case, it's easy to see the solution because here we have a 1 and here we have a 0. So the only way to get this 2 is to take 2 times the first vector. Right? The second one can't contribute anything to that third coordinate. And the same works for the second coordinate. We have a 0 here and a 1 here. So now this vector will not contribute anything, and this one has to take care of getting that 3 right. So we need a 3 here. Right? So that determines our solution. And now, of course, we quickly need to check whether that first coordinate is also correct. So here we have 2 times 1 plus 3 times -1. That is 2 minus 3, so that's -1, and -1 is correct. Okay, so 2, 3 actually solves this, and that means the coordinates of W, with respect to this coordinate system B are 2 and 3. All right. And finally, let's put it all together in part C of that problem. So here we have another coordinate system, B prime. Let me just write that down. So B prime is given as U1 minus U2 and U1 plus U2. So if you write down the actual vectors here, remember B was 1, 0, 1. That first vector was called U1, and -1, 1, 0. That second vector was called U2. So U1 minus U2 is, let's see, 2 minus 1, 1. And U1 plus U2 is 0, 1, 1. Right, so that's our coordinate system B prime. And that is also a system that describes the very same plane in 3D space, because obviously those two vectors are linear combinations of those two, so they all live in the same plane. Right? Those are again linearly independent. So I've just changed the coordinate system. Another question is, if I have a vector that's given in B coordinates, can I determine a description of that same vector in B prime coordinates? And again, the question is, what did you get for that? So let's see, what are the B prime coordinates of my vector V? Here's the URL again. Lots and lots of questions here. All right, 20 more seconds, and then we'll see what you have. All right, so here's your answer. Most of you said the B prime coordinates are -1/2 and 3/2. And again, most of you are right. Okay, so basically, I don't think we need to discuss this. Basically, it's just plugging A and B together. You use A first to get a representation of that vector in canonical coordinates in R3, and then you do the same thing as in B to get the representation in B prime. All right. Maybe a couple questions that have popped up that I can answer. One of you is asking, what does canonical mean? Maybe let me write down that word. So what I am referring to is the canonical coordinates or the canonical basis. That is simply the coordinate system given by the unit vectors. Right? So what I mean is the system U1, U2, and so on up to UN in that order. And that's not the same thing as the U's that we've just had. So maybe let me draw a little line here. All right, so that's often referred to as the canonical basis or the canonical coordinates, or sometimes also the standard basis or standard coordinates. Right, so that's what I mean. And if I do not mention any coordinate system, then this is the one that we'll be using. And we have done so, yeah, up to this point. All right, yes, someone is asking to go to 73A, and actually it was the next point on my list. Let's just see if there's any more questions I should answer immediately. Could we please compute the transformation matrix? We'll talk about that tomorrow, and I'll have plenty of examples about those. Yeah, maybe let's go through H73A actually. Oh, one is, here's an interesting question. Let me quickly answer that. One is asking, and this is about 71A, one is asking whether this here could also be a basis for 71A, and I'm not sure whether he or she is referring to the kernel or the image. But maybe let's discuss why this doesn't make sense for any of those options. So first of all, we know the kernel is two-dimensional. It can't be a basis for the kernel because it has just one vector, right? Can't work. The image is one-dimensional, so we can't rule that out immediately. But obviously that can't be a basis for the image either because it's not contained in R. And the image has to be contained in the codomain. Let me quickly switch to the sheet so that we know what we're talking about. This is the function here, R3 to R. So neither kernel nor basis could work. And furthermore, the zero vector is linearly dependent, right? Because we can find a linear combination that represents the zero vector in multiple ways. Multiply that by anything you want, you always get the zero vector back. So this is linearly dependent. And the linearly dependent vector can't be a basis, right? Or in other words, the zero vector can never be contained in a basis. Can never be part of a basis. So whatever you want, kernel or image, this can't be part of it. Never put the zero vector in a basis. All right, so as you've been asking for it, let's take a quick look at 7.3. And we'll discuss 7.2D tomorrow when I've introduced transformation matrices. So in 7.3 we have a basis and we have a linear mapping that is defined by that basis. And remember, I can define the linear mapping by prescribing the values on any basis I want. And that values can be anything I want. In particular, the values don't have to be a basis, or independent, or different, or not the zero vector. I can also have a zero vector in the image. That's totally fine. Yeah, I just need a basis for the input. The images, that's up to you. So in this case, I have f of 210 is defined to be 110. F of 011 is defined to be 011, so that vector maps to itself. And finally, f of 122 is defined to be 1 to 1. And the first question is, part A, determine f of 2 to 1. And as usual, maybe let's first see what you got here. Let me just switch on that so you can see the URL again. This is very interesting. Votes are coming in a lot slower than before, so I guess some of you did not do that homework. Who would like some more time to think about that before we get the solutions? Okay, maybe let's take a couple minutes so that you can compute that and see what you get. All right, quick show of hands. Who's done? Does anyone need more time? So maybe let's give it one more minute. All right, so here is the result. Most of you said the image is 1, 2, 1, and everyone who voted that is correct. Let's take a quick look at how to solve this, just in case you didn't find the solution. So what we know are the images of these three vectors here, right? And we also know this is a basis because the problem statement says so, or you can convince yourself that those are actually linearly independent if you want. So what we need to do to find the image of that is we need to find a linear combination of the basis vectors to represent this vector here first. So that means we'll have to find coefficients for those three vectors here. Such that the vector we want is represented as a linear combination of those three, right? So in other words, what we want to do is we want to solve a linear system with these three variables here. In this case, it's probably not immediately clear what the solution is, so we'll have to refer to Gaussian elimination. So let's see. Put those here in our matrix, and the right-hand side is the vector 2, 2, 1 that we want to represent. And then we need to do some combinations. Maybe let's first switch those two lines here, because I'd rather have the one as pivot element, just because I'm lazy. I'll just copy the third line. And then I can subtract the new first row from that second row twice. All right, so this is my first pivot element. I want zeros here. So first row is just copied. The second one will become 0, -2, -3, and -2. That's a 3. And there's already a 0 here in the third row, so I'll just leave that unchanged. All right, now I'll have to select one of these two as my new pivot element, and I'd rather have the 1 again, so let me first swap those two lines. Copy the first row. I'll take the third row into the second one, and I'll take the second row into the third one. And now I can just add 2 times the second row to the third. So I get, let's see, I copy the first 2 rows. And here I get 0, 0, 1, and 0. And now I have row echelon form, so I can now solve my equation system. Obviously, the solution is unique, right? My matrix has full rank. So as expected, I get a unique solution. And my solution is, well, lambda 3. I call these lambda 3 red. Maybe let's keep those colors red. So lambda 3 becomes 0. For lambda 2, that was blue. For lambda 2, I have the equation lambda 2 plus 2 lambda 3 is 1. So as lambda 3 is 0, that simply means lambda 2 is 1. And for lambda 1, that was orange. For lambda 1, I get the equation from the first row, lambda 1 plus lambda 2 plus 2 lambda 3 is 2. Again, lambda 3 is 0, lambda 2 is 1, so that means I get lambda 1 plus 1 is 2. And that means lambda 1 is 1. Okay, so in other words, I have determined the coordinates of this vector for the basis B, and those are 1, 1, and 0. And now I can use that to compute the image I want. I can now say, well, the f of this vector is the same thing as f of, let's see. We have this 1 times this first vector here, 2, 1, 0, plus 1 times the second vector, that was 0, 1, 1, plus 0 times the last vector, that was 1, 2, 2. And now I just use linearity to split that all up. And what I get is 1 times f of 2, 1, 0 plus 1 times f of 0, 1, 1 plus, and just let me write that for completeness, 0 times f of 1, 2, 2. And I do know the images of those three vectors because that's how I defined my f, right? It's right here on the sheet. So f of 2, 1, 0 is equal to 1, 1, 0. So that's 1 times 1, 1, 0 plus f of 0, 1, 1 is 0, 1, 1. So 1 times 0, 1, 1. And again, let me just write that for completeness. F of 1, 2, 2 is 1, 2, 1. And I'll just have to put this all together. So I get 1, 2, and 1. And as I said, that's the result that most of you had also computed. Right? And so you can see here, for that part here, to solve this system of linear equations, we need that these vectors that we put in actually form a basis. Because that makes sure that the rank of that matrix will be full, 3 in this case, so we will get a unique solution. For this part here, putting it all together, we need, of course, the linearity. That was that step of f. But whatever these vectors here are does not make a difference. Doesn't matter at all. Could be anything. Doesn't have to be a basis. Right? So that's all we need to do here. Sorry? The last row in this matrix here? Was it 2, 1, 0? Well, this one, right? That's 2, 1, 0? Yeah, that's the image. Right? So here I have f of 210, and that's 110. Right? That is this point here. F of 210 is 110. So here I'm using that to compute the images. Same for the others. And for the blue one, that happens to be, the image happens to be the same vector again, but that's just coincidence. I could use anything I want here. All right? So maybe let me answer one more question. Let's see, is there anything about 3? Don't we have to determine the images in respect to the coordinate system of the codomain first before using them in 7.3a? As long as we're not talking about any coordinate systems, I always refer to the canonical basis, right? And this is the case here in that part A and also in part B and C. There is nothing that says you have to use this and that coordinate system. And of course, if you have a choice, you'd usually use the canonical system. Or if you'd rather use something else, that's fine. You just need to write it down. Yeah, you could also say, I'm using this coordinate system, and here's my answer in these coordinates. Then we have to change the rows back at the end of Gaussian elimination. So in this case, we're only interested in a solution of that system. We're not doing any manipulation of the vectors that we want to use later on. So the order of the linear equations don't make a difference for the solution. That's why we're free to change those, and we don't have to change anything back. And of course, you could also leave them the way you are. You'll get the same result. You might have a little harder time than I had, but that's it. All right. And there's one question I wanted to quickly discuss here. Someone asked, if I have a plane in R2, you remember that in the last problem we had a plane in R2 defined by 2 vectors, and we were discussing the coordinate system spanned by those 2 vectors in R3. And the question is, does that mean that a coordinate system must always include the 0 vector? And the answer is yes. A coordinate system must always include the 0 vector, right? Because it needs to describe a vector space, and that means the only planes that we can use are the ones that include the origin. And of course, the coordinate vectors then also start at the origin, right? You wouldn't, at least in this way, you couldn't define a coordinate system for a plane that did not include the origin, because that's not a vector space, so it doesn't have a basis. And the coordinate system needs to be a basis, first and foremost, and we don't have that if the origin is not contained. You could, of course, do something similar in translated spaces, but we're not going to discuss that. What you'd usually do is translate back and then work there and then undo the translation afterwards. But that's not going to be of much interest in all the applications that we have, so we just stick to vector spaces. And that means all of our coordinate systems always include the origin. That's where the axes start. Okay, lots more questions. I'll go through those until tomorrow and see what I can answer here in class and what I can answer directly online. And then tomorrow we're going to talk about matrix representations and basis transformations. So that's going to be interesting.